Welcome back. We'll start our second part here for the urinary system and start to take a look at the filtration process itself. And so the whole idea of the nephron is that we're going to be able to do a process of filtration. And so we're going to be able to excrete all of the products from the blood that we don't need anymore, get rid of the things that are potentially harmful for us, and allow us to essentially clean the blood itself. And so with that, the first step, as we talked about when we were looking at the nephron, is filtration itself. And so blood coming in through that afferent arteriole starts to come in. And so we have blood entering in through that afferent arteriole there and comes into the glomerulus. And with that, essentially everything that's in the plasma is going to get filtered out. And so the majority of the components that are there gets filtered there, and we're going to take substances that are in the blood and take all of those dissolved substances like our ions, pull those out, many of our hormones, many of our other components that are there, and get that into the capsular space so that it can eventually then head down through the proximal convoluted tubule and go for the next process in terms of secretion and reabsorption that's happening there. So this whole filtration process essentially allows the small things to enter through those membranes, but the larger things are going to get trapped behind. And so things like our cells, our red blood cells, our white blood cells, proteins for the most part, is going to then be allowed to stay in the blood itself. And that's going to then exit through that glomerulus, through the efferent capillaries, and then those capillaries are then going to end up going down through the peritubular capillaries, where we can then start the. And so what we have here is the ability to filter things, and we're going to do a little demonstration here as far as the process goes. And so I have a filter, and I have some coffee, and in that coffee we have the grounds themselves, and we're just going to simply filter things through. And so the coffee grounds are going to represent all of the components of the blood that is too big to make it through that filtration process. So as we keep on pouring through here, our filter is filtering, and we'll see what we have left after this process occurs. So the small components that are within the coffee, and I made essentially a cold brew here, so it's not very strong. And through that, we're going to have the liquid make its way through. And certainly in the kidneys, we're not pulling all of the liquid through the membrane. Some of that liquid is going to remain in and leave as the efferent capillaries themselves. But for our purposes, I'm going to dump everything in there. And I still have some left in terms of the grounds there. But we stopped all of the larger components. We can see it down there in the bottom of the filter. All of the coffee grounds and everything is now out of the coffee, and what we're left with is nice clear fluid below. And so we've taken all of those impurities in terms of the coffee grounds, and we'll just get that out of there. And we can see that they got trapped by the filter. So all of that would be things like our cells within the system inside the blood. All of those cells, all of those large proteins, all of those get trapped here inside the glomerulus and keep on going on through the peritubular capillaries. Other things that may not have had time, all of the things that are there may not have the ability to come out. The majority of the things that are within the blood actually stays in. So 80% or so of the plasma that entered the glomerulus is not actually filtered that particular time through. And so it's going to continue on later on, but it's not going to be filtered out within that first component that's there. From there, we have the continuation of our fluid down through the peritubular capillary. And along the way, we're able to secrete as well as reabsorb. So we can get back the things that we wanted to get back, pull back those components that we wanted to save in there, and we can then also make sure that anything that wasn't able to get in is able to be secreted out of there as well. So if we have filtration occurring, how is it that we can control the process? So when we saw it in the demonstration there, the process of making our filtration occur was just simply with gravity. Gravity was pulling the water down, pulled it through that filter, and that was it. But in terms of our blood is normally under blood pressure. And so we've got some sort of pressure that is occurring inside those blood vessels that's creating the pressure that is there. And if we lower that pressure too much, we're going to have a lower glomerular filtration rate. If we raise that pressure, we're going to get a higher glomerular filtration rate. And so we need to be able to control and make sure that this process doesn't change too much, and make it so that we're also potentially reabsorbing or filtering too much, depending upon how our blood pressure is actually changing. So one of the ways that we can control this process is through the nervous system. So we have baroreceptors that are looking to regulate blood pressure. And we talked about this before, that the kidneys are going to maintain blood pressure through the production of renin. And as renin is released as our blood pressure fluctuates, we're able to then monitor that pressure change and make any kind of adjustments either above or below, but that's going to happen systemically. So in reality, we don't want that to happen necessarily all over the place. We're going to allow this to happen simply in the glomerulus as well. And so this is, again, one of those places where within the body we have only sympathetic control. And so depending upon the amount of sympathetic stimulation that we have, if it goes up or goes down, is going to determine whether we have more or less vasoconstriction. And so those afferent arterioles are going to vasoconstrict or vasodilate based upon that nervous input that's coming in there. And so if we need to increase blood pressure, if we need to decrease blood pressure, we can either vasoconstrict or vasodilate through that process there and allow for us to maintain a normal pressure going through the kidneys themselves. If we get vasoconstriction, that's going to cause a lower filtration rate, and so that's going to cause the blood to start to essentially move through the kidneys without having filtration occurring. We're going to bypass through. So if we're under sympathetic, again, this is our fight or flight. And so if we're in fight or flight, we don't want to be making urine. We don't need to be making urine if we're going to potentially die in a sense. And so our body's going to shut down that filtration process. And so here we have our vasoconstriction. Blood flow coming in is now going to be decreased. And so blood flow goes down. This decreases the amount of blood pressure in our glomerular capillaries. If there's less pressure there, it's just like if we had less pressure going through that filter. So if I kind of was able to tilt the filter on its side per se, it's going to go through the filter for the coffee a lot slower. And so it's going to take more time to go through, and we're not going to have as much filtration, which then decreases our glomerular filtration rate. And that then decreases the amount of filtration that is occurring within the kidneys at that particular period of time. Under parasympathetic control, we have obviously less sympathetic stimulation. So if we're looking at kind of the output of the action potentials, those action potentials then in a sense slow down. So less sympathetic stimulation. This is going to cause those blood vessels to go from the constricted state to the dilated state. And with more dilation, we get more flow, which means we get an increase in our GFR. And so our glomerular filtration rate is going to go up. We're going to be able to filter the blood much more. And so vasodilation allows for the blood to come in. We've got more pressure coming into the glomerulus itself. More pressure equals a greater net filtration pressure, and net filtration pressure is essentially the equivalent of our glomerular filtration rate at that time. And so we're able to monitor and control how much of that pressure is being changed simply by changing the input of blood. If we raise the flow of blood into it, we're going to have an increased ability to do filtration versus if we keep that down. This is also similar to kind of the difference in a sense between making coffee in a drip filter, which is what we showed there, versus making coffee in, say, like a espresso machine. The drip filter is using gravity. The espresso machine is using high pressure. And so we're increasing the pressure multiple times over atmospheric pressure and basically forcing the liquid through the coffee grounds. So we can get a cup of coffee in a much shorter period of time versus if we have to wait around for it to just drip on through. And so we get that coffee produced there. Same kind of thing happens. We can get filtration occurring if we raise that pressure inside that afferent arteriole by having an increased blood flow. So this process here of monitoring what our blood pressure is going to then allow us to maintain that flow into the kidneys themselves. And so if we are under a process where blood pressure is starting to change within that, and if we have a increase in the need for sympathetic output, our vasoconstriction is going to lead to a decrease in glomerular pressure, which leads to a decrease in GFR, which leads to a decrease in the amount of urine that we produce, which then leads to the potential for more water and more salts being left in the body, thereby giving us a increase in arterial blood pressure. And so when our arterial blood pressure is changing in such ways, we're going to kind of limit things. And so that's going to raise our blood pressure up. But as that blood pressure goes up, we cause vasoconstriction to try and alter that process in order to have those changes there as well. And so we have both long-term and short-term adjustments to the blood pressure itself, depending upon what's going on at any given moment. The short-term processes themselves are going to be those things where we go from sitting to standing, we go from doing nothing to starting to run. Those types of processes are going to allow us to very quickly alter our blood pressure and alter them around the kidneys, so we always have a generalized average pressure that is constant within the kidneys themselves, no matter what we're doing. So that change there is going to allow for that to occur there. If we have a change that is too dramatic, that's where then we can potentially, especially if it's a long-term change and pressure goes up and up and up, and so if arterial blood pressure is increasing too much over the long term, that then may lead to potential damage to the kidneys later on, and also alter our ability to do secretion and reabsorption, which is what we'll talk about next time.